So here's a fun little problem. So what I have is a person right here is trying to lift the beam up. So they have the ceiling is 12 feet up, and then so here's the ceiling going across, and so they've gotten a rope, which is held at the top here, and pinned it to the end of this beam. Now this beam is 1,500 pounds, very heavy. So, and this person's trying to lift this thing. So somehow they got it pinned to the end of this beam here. And so this is providing support, and now they're trying to drag this end A to basically take this thing and lift it up. All right. So this beam is 13 feet long, and it's currently at 60 degrees. And the surface is smooth, so there's no friction as they're trying to pull this along. So the person's pulling on this rope here, connected to this other end as they're trying to take this and stand it up, and uh-oh, the rope breaks. All right. So what we want to find, and now when this breaks, this is at basically at rest. So it's just at rest, and then it's going to start to slide back here. And so the problem is find VA here down at the bottom when BC, the rope supporting it, is vertical. So as the rope breaks, this very heavy beam is going to slide back the other way. And when it gets to this rope here is vertical, that's when we want to find what is the velocity here at A. All right. So it's based on position, and the problem involves velocity. So it's an energy problem. All right. So let's take a look at, here's the point where we want to get our answers. So this is my kind of free-ish body diagram. Here's CB, it's vertical, it's 7 foot long. This is a 13 foot long beam. Here's the center of mass, 1,500 pounds acting there. Since the roof is up 12 feet, here's 7 feet down, that makes 5 feet here. If you do the math, that would mean this is a 5, 12, 13 triangle. 5 squared plus 12 squared equals 13 squared. All right. And we want the velocity here at A. All right. Well, so let's start energy. It starts from rest. T1 is 0. No problem. All right. Now, V1. I'm just going to do everything based on ground being the 0 reference. Okay. So, doing that, so let's see what we have to start with. Initially right here in our initial position, so it's 13 feet long, so the center of mass will be 6.5 feet along there. Okay, and it's at 60 degrees. So the initial position is 1,500 pounds, and how high up is it? 16.5 sine of 60. Straightforward. We'll do V2 while we're at it because it's just really simple. If this is 5 feet over here, that means the geometric center is only 2.5 feet up. I don't have to do any algebra to figure that out, or trigonometry as it were. So here's V2. It came real easy. All right. Now we got to do T2, or the kinetic energy in this state. All right. Well, the basic equation for that is the following. 1/2 Ig omega squared plus 1/2 m Vg squared. Okay, center of mass. So we're getting information about the center of mass. And if we have that, then we could use our relative velocity and stuff, and knowing this velocity, knowing omega, we could figure out what VA is. All right, but there's some subtle stuff happening here. All right, so let's start thinking about what's going on. Because I got two unknowns here, omega and Vg. So to solve this problem, I'm going to have to relate these two. All right, so let's start thinking about that. How would I do that? Well, if I look at this thing, what can I tell? This is A is sliding, along this base. So its velocity is in the x-axis. No question. We're going to use the usual xy. So that's going in the x direction. But look at B. It's hanging straight down, and it's rotating off of this chord coming down. So the velocity of B is also in the x-axis. If you have two things, 2 points moving parallel, the only way that's possible is what? It means this isn't, if this is the same velocity as this, if they're in the same direction, it means that VG has to be going in x as well. The whole thing is now just translating. At this instant, the whole thing is translating in the x. That means omega 0. Well, that's nice. That gets rid of that term. I don't have to figure that out. I don't have to relate these two. All right. So note V. So here we have VB and VA are both along the x. This implies omega 0. And if we kind of look at what's happening now, let's just kind of, as this is going down, and let's just look as it gets to this point. As it gets to that point, we have counterclockwise rotation. But as this continues to go over, what's going to happen? It's going to go up. Okay, picture this. As this slides further, this is going to pull the B up higher. So at this point, what we're having is a transition between, look, to get from here to here, we had counterclockwise. As we continue on, we will go clockwise. This is a transition point between omega being counterclockwise and clockwise. So it's right in the middle. It's 0. So we can kind of just see that if we look at this. Okay, so that's just analyzing what we have here. So this is like really good news. Omega 0. And so if it's all going in the x direction, if it's in translation, what does that mean? It means the whole piece has the exact same velocity. So if we get VG, oh, we got VA too. So we don't have to do any work to go here. Omega 0, that means whatever this is, if we went omega cross R to get here, omega 0. So this is the same velocity as VG. Has to be. The moment we realize omega has to be 0, it says VB equals VG equals VA. All right? So that's a huge result. So once we have that, relative to doing T2, it's simply 1/2 VA squared. I put VA in here simply because that's what I care about. Mathematically, it's VG, but they're the same. So I have the 1/2. Ignore this little mark. Mass, 1,500 over 32.2, the VA squared. We simply just need to go in here and solve. That's 14.2 feet per second. Problem done. All right. See you in a moment for another one.